Next to the galaxies and the vast clusters of stars that make them, our solar system is almost nothing. A single grain of dust lit by a yellow star of average size, sitting in an unremarkable corner of an ordinary spiral arm. And yet, if you draw a sphere 100 light-years wide around that grain, you have to account for thousands of stars. Some are so dim that no human eye has ever registered them. Others burn so hard they can be picked out across entire galaxies. Between them drift brown dwarfs that never became stars, frozen, rocky worlds, super-Earths wrapped in thick atmospheres, and objects that don't fit any category we've invented. A few of these worlds might hold life. A few, under the wrong circumstances, could one day be a problem. And every bit of that variety is dwarfed by the Milky Way as a whole. 200 billion stars at minimum, over 1 trillion planets in rough accounting. No civilization is ever going to inventory all of it. Still, the stars sitting closest to home, those we can chart, and some of the things we've learned about them since 2024 would have sounded like fiction to astronomers sitting at their desks in 2018. Time to set out. Roughly 6 light-years out, buried in Ophiuchus, is a small red dwarf that drags itself across our sky faster than any other star we track. That is Barnard's star. And before we get into the rest of it, you have to hear the headline. For a full century, astronomers kept announcing planets around this star, and for a full century, every single claim got taken back. The most recent one collapsed in 2021. If you were following exoplanet news around 2018, you probably remember the splash about a super-Earth of about 3 Earth masses on a 233-day orbit. It turned out not to be there. The signal that looked like a planet was actually the star itself, its own slow activity cycle masquerading as a gravitational tug. Then the story cracked open in a new way. In October 2024, the Espresso spectrograph on the Very Large Telescope in Chile pulled out a real signal. A few months later, in March 2025, the Maroon X instrument on Gemini North, up on Mauna Kea in Hawaii, independently backed it up and added 3 more. As of early 2025, Barnard's star is home to a confirmed family of 4. The tags are B, C, D, and E. Every one of them is small. Each planet carries somewhere between 19 and 34% of Earth's mass. The innermost, designated D, circles at roughly 1.7 million miles from the planet's star, wrapping up a year in 2.34 of ours. The outermost needs fewer than 7 days to do the same. None of them sit in the habitable zone, and the analysis ran deep enough that the research team can say with about 99% confidence that no Earth-mass world exists in the zone where liquid water could pool on a surface. Whatever life-supporting planet Barnard's star might be hiding, if it exists at all, is smaller than our own. The star itself is old, around 10 billion years on the clock, which is more than double the age of the Sun. Mass around 16% of solar, surface around 3100 Kelvin, close to 2830 degrees Fahrenheit. Cool, faint, and on a trajectory pointed at us. Barnard's star is closing in on the Sun at about 68 miles per second. Fast forward 10,000 years or so and it becomes the closest star in the sky, about 3.8 light-years away. Even then you won't pick it out without help. The star is simply too dim for the human eye. A telescope stays mandatory. Here's what's easy to miss. The fact that 2 separate instruments on 2 different mountains on 2 different continents, working with teams that weren't coordinating their observations, landed on the same 4 sub-Earth mass planets around a 6 light-year distant red dwarf. That level of confirmation simply did not exist a decade ago. The stars haven't changed. We got better. Now, turn that around. Face the other side of the Sun. What sits there is pretty much the exact photographic negative of the star we just left. Sirius, brightest star in the entire night sky, 8.6 light-years from Earth. Naked eye, it reads as one white-hot pinprick. Put a decent telescope on it and the single point splits in 2. The dominant component, Sirius A, runs around 2 solar masses and about 70% larger in diameter than the Sun. Surface temperature lands near 10,000 Kelvin, which is why it registers as that bluish white. In raw energy output, Sirius A pumps out about 25 times what our Sun puts out. The companion, Sirius B, is a white dwarf. Its physical size matches Earth roughly, radius close to 3,700 miles, but it's packing nearly a full solar mass of matter into that volume. A teaspoon of the stuff would weigh a ton on a kitchen counter. Surface temperature runs around 25,000 Kelvin, hot enough that most of its output comes out as ultraviolet. That alone makes Sirius B the closest white dwarf to our planet. The two orbit a shared center of mass every 50 years on a stretched ellipse. At their widest, the pair sits about 31 astronomical units apart. At their tightest, closer to 8. Despite decades of hunting, Hubble, VLT, Sphere, Keck, and TESS all taking their turns, no confirmed planet has shown up in this system. A 2015 campaign using the VLT Survey telescope ruled out anything more massive than 4 Jupiters anywhere close in. Sirius B has been imaged with Hubble and Sphere. Those observations cap any companion there at roughly 1 to 2 Jupiter masses. There's a possible reason for the emptiness. Sirius B was the heavier of the two originally, a 5 solar mass star burning hot and blue. Roughly 120 million years ago, it ran through its core fuel, bloated into a red giant, blew off its outer shell as a planetary nebula, and collapsed into the Earth-sized emperor we see today. That's a violent transition. A young protoplanetary disk, or any planets that had already formed, would have been scorched, stripped, or kicked out of the system. Sirius is still inching closer. Over the coming 60,000 years, it will tighten to a minimum distance of about 7.5 light-years, brightening noticeably in our sky, and then begin pulling away again. Roughly 660 million years from now, Sirius A will meet the same end its companion already met. One brief, enormous flare, thousands of times brighter than the star we see tonight, and then Sirius disappears from the sky for good. Leaving behind the blazing Sirius neighborhood, a course correction brings us to something much quieter. About 14 light-years out from Earth and Ophiuchus again sits a small red dwarf named Wolf 1061. The star has a few other catalog numbers too, but the Wolf designation is the one that stuck. In physical terms, the star is modest, radius about 30% of the Sun's, mass around a quarter of solar, surface temperature near 3,300 Kelvin, roughly 5,430 degrees Fahrenheit. Its total light output is a touch over 1/10 of 1% of the Sun's. You won't see Wolf 1061 with the naked eye from anywhere on Earth. What makes it worth the trip is the planetary lineup around it. 3 confirmed worlds, cataloged B, C, and D. All 3 thought to be rocky, each on a completely different kind of orbit. Wolf 1061b rides innermost, orbital distance of roughly 0.038 astronomical units, which in ordinary terms is about 3.5 million miles from the star. A full year there is 5 Earth days. Mass between 1.5 and 2 of ours, radius about 20% larger, almost certainly tidally locked, meaning one face is permanently baked. Any atmosphere it ever had was peeled off long ago by stellar wind and flare activity. This is not a habitable place, not even close. And then there's Wolf 1061c. For a stretch of years after its discovery in 2015, this one was near the top of the list of the most interesting rocky planets ever found. Closer to Earth than Proxima b, and at the time, apparently sitting right inside the habitable zone. The numbers: orbital radius of about 0.084 AU, year length of 17.9 Earth days, minimum mass between 3 and 4 Earths, which puts it in super-Earth territory, predicted radius around 1.6 times ours, surface gravity, if it really is rocky, roughly 60% stronger than what your feet feel right now. Then came the reassessment. In 2017, a team led by Stephen Kane at San Francisco State University took a closer look at the host star and recalculated the edges of the habitable zone. Their conclusion: Wolf 1061c isn't comfortably inside it. It's parked on the hot inner boundary. Kane's word for it in print was that the planet looks suspiciously like a runaway greenhouse, the Venus edge. On top of that, Wolf 1061c's orbital parameters shift on much shorter timescales than Earth's do, which hints at violent swings between freezing and boiling climate states instead of the gentle cycles our planet enjoys. Is there liquid water? Possibly, with the right atmospheric chemistry at the right moment in its orbital cycle on a well-shaped pole. Nothing about Wolf 1061 is the sure thing it looked like in 2015, but it's still among the closest rocky worlds that aren't outright ruled out, and that keeps it high on every follow-up target list. The outer member of the trio, Wolf 1061d, runs a noticeably stretched orbit between about 0.21 and 0.73 AU from the star. Its mass clocks in somewhere around 7 or 8 times Earth's. Far too cold for surface water at those distances, but scientifically it's valuable because the range of conditions it passes through gives us data we barely have on how red dwarf planetary systems evolve. Wolf 1061 also happens to sit right on the boundary of something bigger. The solar system is currently traveling through a thin bubble of warm hydrogen called the local interstellar cloud. This star marks one of the walls. We'll come back to that structure later in the episode. Push farther out, about 27 light-years away, down in the southern constellation Columbae, there's a red dwarf doing something in the neighborhood isn't supposed to allow. The star is cataloged AP Columbae, and the first weird thing about it is its age. AP Columbae is young. When the Australian National University team first studied it carefully back in 2011, their analysis landed on an age of around 40 million years. That would have made it the closest pre-main sequence star ever found, a stellar newborn sitting practically next door. Later work tightened the picture. Based on the star's shared motion with the AB Doradus moving group, a cluster of young stars that drift through the galaxy together, current estimates put AP Columbae somewhere between 130 and 200 million years old. Still young by stellar standards, still a fraction of the Sun's 4.6 billion, but not quite the freshly minted object the 2011 announcement described. Physically, it's modest, about 26% of the Sun's mass, 29% of its radius, and barely 0.5% of its luminosity. Surface temperature close to 3000 Kelvin, roughly 4,940 degrees Fahrenheit. What stands out is that it's putting out about 4 times more energy than a red dwarf of that size should, and its radius comes in nearly twice what stellar structure theory predicts. The odd numbers point it straight at lithium. Spectra of AP Columbae show an abundance of it that shouldn't be possible in a settled main sequence star. Lithium doesn't survive long in stellar cores. As soon as hydrogen fusion really gets going, lithium burns out. If the element is still there, the star hasn't fully turned on yet. AP Columbae is still contracting under its own gravity, still finding hydrostatic equilibrium. That unsettled state expresses itself as flaring. AP Columbae is classified as a UV SETI flare star, which means its brightness can leap by a factor of 10 within minutes. Anything orbiting close enough to sit in a habitable zone would be getting hammered. Atmospheric loss from stellar wind, UV flux spiking to sterilizing levels, and no buffer to speak of. So far, observations show no massive planets within about 4.5 astronomical units of the star. That matches theory. AP Columbae is probably too young for fully formed planets yet, and that is precisely why it's a scientific prize. The star gives us a close-up, high-detail view of what stellar youth actually looks like, and what a forming planetary system has to withstand in the first couple 100 million years of its existence. One last detail before we move on. AP Columbae didn't form where it is now. Its galactic motion suggests it was born in a star cluster called IC 2391, about 450 light-years from its current position. Something in that cluster, probably a supernova, gave it a gravitational kick that punted it out of its birthplace. Since then, it's been coasting toward our part of the galaxy, a runaway. Farther out again, about 37 light-years from home, in the constellation Vela, an orange K-type star quietly keeps to itself. Catalog name Gliese 370, also listed as HD 85512. Smaller than the Sun, cooler, roughly a billion years older than our star, and remarkably calm. Very little magnetic activity, very few flares, the kind of host star exoplanet hunters love. Back in 2011, data from the HARPS spectrograph pointed at a companion called HD 85512b. Super-Earth territory, minimum mass around 3.6 Earths, orbital period a little over 50 days. At the moment of announcement, the planet looked extraordinary, one of the most Earth-like worlds ever found, parked near the edge of its star's habitable zone, with a host star that wasn't going to blast it with radiation. On paper, it had everything. The early habitability modeling suggested that if the planet carried cloud cover above 50%, its surface could hold temperatures in the neighborhood of 77 degrees Fahrenheit. That framing ran in headlines around the world for a while. A slightly warm version of Earth, 37 light-years away. The story got quieter. 2 years later, updated habitable zone models pushed HD 85512b out of the liquid water region and into territory too hot to keep surface oceans stable. The stellar flux the planet receives, about 1.86 times Earth's, sits closer to Venus's 1.92 than anything you'd want to walk on. Then in 2023, a reanalysis of the original radial velocity data cast serious doubt on whether the planet exists at all. The signal may have come from the star itself, not a companion. In most current habitable exoplanet catalogs, HD 85512b is listed under the heading of false starts, a candidate that shone bright on initial measurement and dimmed under better instruments. That pattern shows up again and again. Every few years, the list of the most promising nearby exoplanets reshuffles. Something that topped the 2011 rankings is gone by 2023. Something ruled out in the 1980s, a planet around Barnard's star, for example, comes back under a different name in 2024, with better data behind it. The stars haven't moved. Our measurements of them have. Pause here and look around. We've now crossed more than 50 light-years from home. That sphere holds over 1,000 stars. Most are solitary. A healthy share are binaries. And one of them, in the constellation Gemini, refuses to fit into any simple category. Castor, second brightest star in Gemini after Pollux, and the 23rd brightest star in the entire night sky. Distance from Earth about 51 light-years. To the naked eye, 1 point of light. Put a small telescope on it and it splits into 2. Keep looking harder and each of those 2 resolves into a spectroscopic binary, a pair of stars too close together to separate visually, but unmistakable in their spectra. And then there's a third, fainter pair orbiting the whole arrangement from far out. 6 stars, 1 gravitationally bound system. Apollo-era textbooks called Castor a quadruple. We know it now as a sextuple. The 2 dominant components, Castor A and Castor B, are hot 8-type white stars, each more massive and more luminous than the Sun, and each carrying a red dwarf companion on a tight inner orbit. The 2 primaries themselves sit about 110 astronomical units apart, which translates to roughly 10.2 billion miles. They swing around their shared center of mass on a 445-year orbit. Further out, roughly 1,000 AU from the AB pair, lies Castor C, also known as YY Geminorum. 2 red dwarfs, each about 0.6 solar masses, surface temperatures roughly 6,330 degrees Fahrenheit. They orbit so tightly, separated by just a handful of stellar radii, that they complete 1 loop around each other in under 20 hours, and they eclipse each other every time they do it. The Castor C pair, as a unit, takes roughly 14,000 years to orbit the AB pair once. As of today, no confirmed exoplanets exist anywhere in Castor. But in 2018, astronomers noticed small variations in Castor C's orbital period consistent with a brown dwarf. Something about 49 Jupiter masses, orbiting at roughly 14 AU with a 54-year period. It's still a candidate, not yet promoted to confirmed. If any rocky planets do circle the red dwarfs deep inside Castor C, the sky over their surface would be one of the strangest anywhere in our catalog. 2 crimson suns almost touching, sweeping across one half of the sky in under a day. Off in the other direction, 2 blue-white stars burning hundreds of times brighter than our full moon. No true night on such a world, just a perpetual shifting twilight. Every star we visited so far, Barnard's, Sirius, Wolf 1061, AP Columbae, Gliese 370, Castor sits inside one very large structure, a roughly spherical cavity in the interstellar medium, around 300 light-years across, filled with hot, thin gas. Astronomers call it the local bubble. The local bubble is a scar. Between 10 and 15 million years ago, a chain of supernova explosions went off in this part of the galaxy. The blast waves from those dying stars swept most of the cold gas out of the neighborhood, leaving behind a cavity of hot, diffuse plasma, temperatures close to 1 million Kelvin, and densities roughly 10 times lower than the galactic average. Plasma that hot glows in X-rays. The reason you aren't being cooked by it at this moment is layered protection. The sun's magnetic field, Earth's magnetic field, and the column of atmosphere over your head together deflect and absorb the hard radiation before it reaches the ground. Take away any of those shields and life on the surface looks very different. The solar system has spent about the last 10,000 years drifting through a smaller feature within the local bubble, the local interstellar cloud, roughly 30 light-years across. Warmer, thinner hydrogen around 7,000 Kelvin. We're close to its far edge now. In about another 2,000 years, the sun exits this cloud and enters something even less dense and even hotter. Reminder worth internalizing. The interstellar medium is not empty. It has weather, currents, a history, and bits of it leave traces in unexpected places. Iron-60, a radioactive isotope that only gets produced in supernova explosions, has been pulled out of Antarctic ice cores. That iron came from the local interstellar cloud. Somewhere in the deep past, a nearby star detonated, and some fraction of its expelled material ended up frozen at the bottom of this world. The local bubble doesn't sit alone either. Other bubbles border it. One of the larger ones, centered near Antares and roughly 500 light-years from us, has been slowly pressing against our cavity for millions of years. Where the two shells meet and compress, the gas piles up into dense walls. The solar system on its current trajectory reaches those walls in a few tens of millions of years. Clouds of hot gas, open star clusters, giant nebulae, streams of stars moving together in coordinated drift across tens of thousands of light years. Every one of these structures belongs to one bigger system, the Milky Way galaxy. And the Milky Way is just one of several 100 billion galaxies. Those galaxies don't scatter evenly. They cluster into filaments and walls that stretch billions of light years across. That pattern is the large-scale structure of the universe, the cosmic web. Inside that web, along one filament in one galaxy, on one arm of that galaxy, inside one bubble of hot plasma, inside one cloud of thin hydrogen, around one ordinary yellow star, is this planet. And on this planet, a species that has only been capable of detecting worlds around other stars for about 30 years now, knows there are 4 of them around Barnard's star, 6 stars locked together in the Castor system, 1,000 stars within 50 light-years of home, and uncounted worlds beyond. Apollo-era astronomers knew essentially none of that. What they had was a theory, a handful of nearby stars they could resolve in a telescope, and a catalog of guesses. The first confirmed exoplanet around a sun-like star didn't arrive until 1995. As of this year, the confirmed count has crossed 6,000, and it's still climbing fast. We are in the most productive stretch of planet hunting that has ever happened. The closest stars, the ones we just walked past, are the ones returning the most detailed data of all. Nobody alive today has seen another Earth. Not yet. But the instruments that would be capable of finding one are being built, launched, and calibrated while this video plays. The next decade of results from JWST, Gaia, Maroon X, Espresso, and whatever generation of instruments replaces them is going to rewrite this script again, probably more than once. What we know about the solar neighborhood in 2026 is going to sound quaint in 2046. That's the deal with science. Every version of the map is provisional. Every version is better than the one before it.